Hi everyone, good day. Are you ready for another Math Venture with Teacher Rev? Let's start our statistics learning journey.
In probability, when we do an activity that can be repeatedly done under similar conditions, we are actually doing an experiment. Can you give an example? Things that we do repeatedly. The one that you studied when you were in grade 8, remember? One classic example is tossing a coin. Can you try? Kindly get a coin. Let's try at my count. Ready? And go. What do you think is the result? Let's see if you guessed it right. In this case, the result is a head. The result of a trial in an experiment is called an outcome. Since the experiment of tossing a coin resulted with a head, then head is an outcome. How about you? What result did you get? I'm sure the results vary. If you repeat this activity, is the result always a head? If your answer is no, I agree with you. What other results did you get? I'm sure some got a tail. What about when you spin a coin? What are the possible results? If your answer is a head or tail, then your answer is correct. Note that the result of all possible outcomes in an experiment is called a sample space. And in this case, the sample space is either a head or tail. Let's have another experiment. When we roll a die, what is the sample space? Remember, sample space is the result of all outcomes in an experiment. If your answers are 1, 2, 3, 4, 5, or 6, your answer is correct. Thus, the sample space of rolling a die are 1, 2, 3, 4, 5, and 6, because these are the possible outcomes when rolling a die.
Wow, so what did we learn from the video? First, we learned that an experiment is an activity which can be done repeatedly, okay, as what you've seen in the examples shown earlier. We also learned that a sample space is the set of all possible outcomes in an experiment, and it is denoted by a symbol S. So meaning, tossing a coin and throwing a die are experiments. The sample space in tossing a coin, you can either have a head or a tail. Of course, the outcome will be unpredictable, but we are sure that there are the possible outcomes would just be a head or a tail. When we throw a die, there are 6 possible outcomes. It can either be 1, 2, 3, 4, 5, or 6. But again, the outcomes may be unpredictable. But we're not going to stop with that. We also have what we call an event. When you toss a coin and getting a head is an event. Or getting a tail is also an event. An event is a subset of a sample space. It is a collection of one or more outcomes considered as a group. Okay, so another thing, later we're going to have more example of that. A sample point is an element of the sample space. So meaning, it is an element that can be found in a sample space. Okay, let's have example. If we have an experiment, we have as a sample space, we have the event, and we have the sample point. The experiment would be tossing a coin. In tossing a coin, the sample space is getting a head or a tail. The event is getting a head. Then the sample point will just be head because the sample point is dependent of the event. Remember, getting a head is a subset of a sample space because in the sample space, you either have a head or a tail, which is written as HT. Okay, let's have another one. What about rolling a die? Rolling a die, we have the sample space. What would be the sample space in rolling a die? We have a 1, 2, 3, 4, 5, or 6. So in this case, there are 2 items in the sample space. In this case, there are 6 items in the sample space. Then let's have an event. When you roll a die, an event could be getting an even number. So getting an even number would mean what would be our sample points. The sample points must come from a sample space. So the sample points will be 2, 4, or 6. There are 3 items in our sample point. There is only 1 item in our sample points in the first case. So is this clear? Let's have another one. Same experiment, rolling a die, same sample space of course, but this time let's have getting a prime number. Take note that a prime number is a number whose factor is 1 in itself, but 1 is neither prime nor composite. So therefore, what are the sample points? Again, the sample points will come from the sample space because an event is a subset of a sample space. So therefore, getting a prime would mean having 2, 3, or 5. Are you getting that? Next. Okay, I'm getting that, teacher. What else? How about if the experiment is drawing a card from a deck of cards? Okay, I'm not going to list all the sample space there because that's a lot. I'm not going to list all the sample space there because that's a lot. Let me just have it this way. How many items do we have in the sample space? Exactly, there are 52 cards in the sample space, so there are 52 items in the sample space. Now, the event would be getting a 2. Okay, what sample points would that be? Here I have 3. Here I have 2 of hearts, 2 of diamonds, 2 of clubs, and then 2 of spade. Wow, okay. So how many? I have 4 items in the sample space. But again, these are from the sample point. So I hope you can differentiate an experiment and an event, and a sample space and a sample point. Okay. Now, with all the given examples, let's try to answer what we had earlier. We said that if you have 3 shirts and 4 pairs of pants to choose for your OOTD, how many different attires do you have? First, if I consider the first shirt, I can actually pair the first shirts with any of the 4 pairs of pants. And I will definitely have a different set of attire. So, if I have the pink shirt with the blue pants, with the pink pants, with the gray pants, or with the yellow pants, I have 4 different attires. That is considering the first shirt only, but I have 3. So the second shirt, I can still pair it up with the 4 pants and have a different attire from the first set of attires I have, because this time I'll be pairing the yellow shirt with the blue pants, with the pink pants, gray, and the yellow. So that's a totally different attire. And of course, if I have the last shirt, which is the blue shirt, I can pair it with the 4 pants as well. So I'm going to have another set of different attires. This time I'm going to have the blue shirt and the blue pants, the blue shirt and the pink pants. We have the gray pants, blue with the yellow pants. So how many attires, how many different attires could I have for my OOTD? If I consider the pink, I can pair the 4 pants with the pink shirt. I can pair the 4 pants with the yellow shirt, and I can pair the 4 pants with the blue shirt. So how many total items do I have? Exactly, all in all, I have 12 choices for my OOTD. Wow! So basically, we don't need a lot in life to be able to survive. We can actually have 3 shirts and 4 pairs of pants and have totally 12 totally different attires. Oh, how wonderful is that, right? So, if that's the case, what did we do here? We know that for every shirt that we have, we can actually pair it with the set of pants that we have. If we are going to analyze, we have 3 choices for the shirts and 4 choices for the pants. We can just multiply them 3 times 4 and we're going to have what? 12. Exactly. There are 12 attires to choose from for my OOTD, just like what we have in this diagram. This diagram is what we call a tree diagram. Maybe I don't have to explain why we call it tree diagram, basically because we can because it branches out. Yan. Okay. So, the tree diagram help us understand, but basically, from the tree diagram, we derive a simpler process of simply multiplying the 3 and 4 because every shirt can be paired with a 4 pants. So, if I have 3 shirts, I can pair it with 4 pants, then it's simply multiplication. That's why we arrive at what we call the fundamental principle of counting, or FPC. Let me define it for you. The group of K experiment, if the first can be done in n sub 1 ways, just like the shirts, the second can be done, the first can be done in n sub 1 ways, the second can be done in n sub 2 ways, just like the pants, the pairs of pants, and the third can be done in n sub 3 ways. Let's say I'm going to add another one, that would be pairs of shoes, until kth experiments. Then the total number of ways in which the K experiments can be done in that order can be defined by multiplying the number of ways in each event. That means if I'm going to add one more event, I can actually have pairs of earrings. If that's the case, then, for instance, the shirt I have, just like earlier, 3 shirts, 4 pairs of pants, let's say 2 pairs of shoes, and 5 pairs of earrings. If I'm going to multiply that, 3 times 4 times 2 times 5, that would be 120 different attires. So basically, the fundamental principles of counting is simply multiply the number of ways how the first, the second, the third, or the fifth, or the kth experiment will be conducted. Are you getting that? Okay, let's continue. In this case, the 12 choices that we have is the sample space. After knowing about fundamental principles of counting, let's apply this concept. First, how many possible outcomes are there for the gender of 3 children in the family? We know that we have the firstborn, the secondborn, and the thirdborn. There are 2 ways that the firstborn will come out. It's either the firstborn is a male or a female. Also, the secondborn, it can be male or female, as well as the thirdborn, it can be male or female. If we're going to use the tree diagram for the gender, let's start with the first sibling, or the eldest. The eldest could either be male or female. So, if it's male, there's a possibility that the second child will be male or female. If the first child is female, then there's also a possibility that the second child is also a male or a female. Now, let's talk about the third sibling. With the third child, we know that if the first is male, the second is male, 2 possibilities will happen. The third can be male or female. And also, if the first is male and the second is female, again, the third could also be male or female. The same thing goes if the first child is female, the second is male, then the third could be male or female. And last, if the first child is female, the second child is also female, the third child can be male or another female. So in that case, if we are going to consider the gender of the 3 children in the family, then we're going to have either male or female for the firstborn. And on the secondborn, we're going to branch out. If that's a male, then we have male or female. If that's a female, then we have male or female. Same thing goes with the rest. With the thirdborn, or the youngest. The youngest could either be male or female for any category. Okay, so for any branching, we have male or female, and so on. Same with the other parts. So basically, if you're going to look at this scenario, we can actually have all male. We can have 2 males, and the youngest is a female. We can have 2 males, but the female is the middle child. We can have 1 male, and then followed by 2 females. We can also have the female as the eldest, then followed by 2 males. We can also have the female, then we have the male and the female in the youngest. We can also have the female eldest, female middle, and male youngest. And last, we could also have all female. Now, how many possible outcomes do we have? We have 8 possible outcomes, and this is what we call the sample space. If we are going to relate it to our previous discussion, we can say that getting the gender of 3 children in the family is the experiment, and the sample space would be the 8 outcomes that we have here. So if we're going to play with it, we can say that there's only 1 out of the 8 chances that all children will be male. Same as with female. So this is how we answer the problem. Now, that is using the tree diagram. But what if we are going to use the fundamental principles of counting, or the FPC? We can actually do it this way. We have the firstborn, secondborn, and the thirdborn, or the eldest, the middle, the youngest. We know that the gender of the firstborn could either be male or female. So there are 2 chances for the gender. Same as with the secondborn and the thirdborn. Therefore, if that's the case, every first child can be paired with the gender of the second child, and every gender of the second child can be paired with every gender of the third child. That means we can actually multiply it using the fundamental principle of counting. So we have 2 times 2 times 2. That would leave us with 8. There are 8 possible outcomes in the sample space. Therefore, there are 8 possible outcomes for the gender of 3 children in the family. Actually, the fundamental principles of counting made it easier for us to solve problems such as number 2. Let's have example 2. Mr. Buendia planned on eating on a food chain which has a promo for a meal for 150. The one listed below are the choices. How many possible meal sets can Mr. Buendia form if a set meal is made of an appetizer, a sandwich, a medium-sized drink, and a dessert? If that's the case, if we have an appetizer, then we're going to have a sandwich as well, and the drinks, and the dessert. How many choices do we have for the appetizer? We have 3 choices for the appetizer. So let's key in 3 here. Multiplied by how many choices do we have for the sandwich? We also have 3 choices. It can either be chicken, shrimp, or hamburger. How many choices do we have for the drinks? We have 3 choices, a juice, a shake, or a coffee. And for the dessert, we have 2 choices. Either we have an ice cream or cake. Multiplying all these values, 3 times 3 times 3 times 2, that would be equal to 54. So, there are 54 possible meal sets that Mr. Buendia can form if a set is made of an appetizer, a sandwich, a medium-sized drink, and a dessert. That's a lot, right? That's a lot to choose from. That's the reason why sometimes most of us have difficulty identifying what we want if we have a lot of choices, because if we have a lot of choices, it means that there's a lot of possible outcomes that we can come up with, and that made it more difficult for us to choose. Okay, so have patience if you're lined up in a fast food store and people are still taking time to look at the choices in the menu. A lot of arrangements. Okay, so and a lot of choices. Let's continue with the third example. If 2 dice are tossed, how many possible outcomes can we have? So basically, we have the first die and the second die. So the first die, if you roll the first die, you have how many choices for the first die? Exactly, there are 6 choices in the first die. Also, there are 6 choices in the second die. That means if you multiply these 2 items, we all in all have 36 possible outcomes when we toss a die. Can you give some possible? If I'm going to give some possible outcomes, I can have 1 and 1 as an outcome. I can also have 2 and 1. I can also have 1 and 2, 3 and 3, and you can name a lot more. If I name 4 already out of the 36, then you can still name 32 different pairs of outcomes. Using the integers 1, 3, 5, 7, and 9, how many 2-digit numbers can be formed if A, repetition is allowed? When we say repetition is allowed, it means that you can repeat the numbers. Let's go back to the problem. We are allowed to use the integers 1, 3, 5, 7, 9. Therefore, we're allowed to use 5 integers. And we are going to form 2-digit numbers. So if we're going to form 2-digit numbers, that means we have the tens and the ones. question, if repetition is allowed and we are allowed to use any of the 5 numbers, for the tens digit, how many choices do we have? We have 5 choices for the tens digit. As well as the second digit, how many choices do we have if repetition is allowed? Meaning, whatever we use on the tens digit, we can still use it on the ones digit. We have 5 choices. Therefore, 5 times 5 is what? 25. Very good. So, that means using the integers 1, 3, 5, 7, and 9, we can actually form 25 two-digit numbers with repetition allowed. Now, what if we are supposed to answer letter B? This time, repetition is not allowed. So again, we're going to form two-digit numbers, but this time, we're not allowed to repeat the numbers that we're going to use. So in the tens digit, definitely we have 5 choices, but in the ones digit, whatever we use in the tens digit cannot be used in the ones digit anymore. So out of the 5 integers, if we already used 1, how many choices do we have for the ones digit? We have 4 choices for the ones digit. That means 5 times 4, multiplying this, we only have 20 items in our sample space. Okay, let's consider the given number. What numbers repeat? If we're going to form this, we have 11, 33, 55, 77, and 99. So these are the two-digit numbers. Let's count. We have 1, 2, 3, 4, and 5. Since there are 5 items that repeats, remember, without repetition, we have 20 only. With repetition, we have 25. From the 25, removing the number that repeats, we have 20. That's how we actually relate these two values. We can simply get 25 minus the item that repeats, which is 5, equals 20. That will give us an answer to letter B. That's another way of getting the answer to letter B. Do you get that? So, let's try another scenario. What if we're asked to identify first a 3-digit number this time? But you're supposed to use the same numbers, 1, 3, 5, 7, 9. We're going to form a 3-digit number, and this time, let's answer letter A. We stick to that. Repetition is allowed. So we have the hundreds digit, the tens digit, and the ones digit. So we have 3 blanks. If repetition is allowed, how many choices do we have for the hundreds place? If we are supposed to use the integers given, yes, we have 5 choices. 5 choices also for the tens digit and 5 choices also for the ones digit. That will give us how much? 125. So there are 125 3-digit numbers that we can form if repetition is allowed. Now let's go for B. It says in B we have to form a 3-digit number using the given integers, but this time repetition is not allowed. So if that's the case, if repetition is not allowed, what we're supposed to do is to first get the value. That would be 5. We have 5 choices from for the hundreds place, but since 1 out of the 5 is already used, we only have 4 choices for the tens place. And since 2 of the numbers are already used and we cannot use that number again because repetition is not allowed, that leaves us 3 choices for the ones place. Now, we can get the 3-digit number, the number of 3-digit numbers by multiplying 5 times 4 times 3, which is equal to 60. So there are 60 numbers, 60 numbers where repetition is not allowed. We can form 63-digit numbers out of the given 5 integers where repetition is not allowed. So I hope you understand everything. And I need you to identify how you feel with our discussion today. But with this thing, enjoy your weekend. God bless you all. I hope you learned something from our discussion. This had been a great learning adventure. So, see you next time on another Math Venture with Teacher Rev. Remember, don't stop until you're proud. Learning math takes time. Bye!